Hi folks, we're going to take a look at the solution to number 19 on page 265. So they give us this right angle triangle and they want us to find the angle theta that's going to maximize the perimeter of this right angle triangle that has got a hypotenuse of 12. Okay, so first of all, what we're trying to, in this case here, maximize is the perimeter, which is just going to be x plus y plus 12. Okay, and as we've seen many times, two variables, so we need to write this in terms of one variable. Now, I could use Pythagoras to write y in terms of x or x in terms of y, but what I'm looking for is an angle, so it might make more sense to just write everything in terms of theta. Okay, which should be pretty easy since it's a right angle triangle. So here, if I take start with the x, adjacent hypotenuse, so I should work with cosine, so cos theta equals x over 12, so x is just equal to 12 cos theta. And then I'll do the same thing with y, but this time I'll use sine. And so we have y equals 12 sine theta. Okay, and so now I can just put that into my equation. So we've got 12 cos theta plus 12 sine theta plus 12. Okay, and since we're working in a right angle triangle, we know that theta is going to lie between 0 and pi over 2. Okay, and it's non-inclusive since if theta is 0, there's no triangle, and similarly for pi over 2. Okay, so we don't have a closed interval situation. Next step, find the critical numbers here. So we take the derivative, so derivative of cos is negative sine, so we end up with negative 12 sine theta. And then here we have plus derivative of sine is just cos, so 12 cos theta, and of course derivative of 12 is just 0. Okay, what we want to do is set this equal to 0. And here, first and foremost, I'll divide both sides by 12, make my life a little easier by getting rid of those coefficients, and then I'll bring the minus sine theta to the other side. Now you might think, why am I doing that? Well, negative sine theta plus cos theta, there isn't really anything nice I can use to simplify that. You know, I certainly don't want to bring in the Pythagorean identities and bring in square roots if I don't have to, and you know, I don't want to use any of the correlated angles because I don't want a theta plus or minus pi over 2. But hopefully we remember that we know exactly when sine theta is equal to cos theta. Okay, and in particular, if we're only living in the domain from 0 to pi over 2, this occurs at pi over 4. So we know that theta equaling pi over 4 gives us the same value for both sine and cosine. Okay, so there's our critical number in our interval. Let's now test to see if that indeed gives us a maximum. So we know we're only interested from 0 to pi over 2, and so we've got pi over 4. And so here, you know, I'll pick some really small numbers. So let's pick, so there's my derivative. Let me put 0.1. Okay, so I've got negative 12 times sine of 0.1, okay, plus 12 times cos of 0.1, and that gives us a positive number, so good start. And let's pick something, so this is smaller than 1, so I'll pick theta equals 1 to test the other interval. So we've got negative 12 times sine of 1 plus 12 times cos of 1, and we end up with a negative number. Okay, so what we have is that on the interval of interest, we see that it's continually increasing to pi over 4 and then continually decreasing. So this is indeed an absolute maximum on that interval. Okay, so there's our value. Let's go back to the question and see what they actually want. It says calculate the measures of the unknown angles in the triangle that will maximize its perimeter. So I guess we actually have to find both angles, but since one is pi over 4 and it's a right angle triangle, the other one has to be pi over 4. So both angles are pi over 4. Okay, now think about it, that's not too surprising, because if you draw a triangle with an angle of pi over 4, okay, it's just half of a square. Okay, and we've seen before that rectangle you know, an optimized rectangle is often a square. So here it looks like we have this optimized triangle, which is one with angles of pi over 4. Okay, that's it for this one.